So in the tutorial 2, you have a problem. You are given a pipe flow problem. Now this describes actually the mesh that you created earlier. So it has a length. The pipe has a length of 0.8 meters and a diameter of 0.1 meter, and the fluid inside the pipe has a coefficient of viscosity of 2 to 10 to the minus 3 and a density of 1 kilogram per meter cube, and the inlet velocity is given as 1 meters per second. And what you're supposed to do to calculate the Reynolds number, then solve the problem using Fluent and plot velocity profiles, validate results, and repeat the same thing for a increased mesh density. So you can say in the problem description that you in a laminar fluid flow you have a developing flow region and a fully developed flow region. So the 0.8 meter length will accommodate both the fluid flow developing region as well as the fully developed fluid flow region. And if you go back to your ANSYS workbench, you will now see that there are two ticks against the geometry and mesh. That means you have created the geometry and the mesh. Then what you have to do now is to bring ANSYS on to play. So to do that, you need to go to setup to bring the Fluent launcher, and again all the instructions are given here so that you can run through the simulation step by step. So the first thing that you have to do is to create you have got the mesh and you need to display the mesh. You can display the mesh in Fluent. There is a distinction between ANSYS workbench and Fluent. So ANSYS is the platform on which you are running these few pieces of software, meaning you create the geometry using a CAD software. Then you create the problem, or you do the setup of the CFD problem using the CFD software called Fluent. So the screen you see here is actually Fluent. It's not. It's sitting on ANSYS, but it's a separate software. And then you already created your inlet, outlet, and wall in the named selections earlier, so you should see them. Then what you are doing is you are creating boundary conditions here, and boundary. You know what boundary conditions are. You know the inlets, outlets, walls, etc. And then you also give properties to materials here. And then you give operating conditions as well. So what you have to do is to fully define your physics problem, and then once you have defined the problem, you give the solution method. That is you are setting up the CFD simulation. So this bit in the tree, you will see the boundary conditions, etc. Now these are solution methods, and then what you have to do, you give the solution method, then you initialize. In the initialization, what you do is you give initial values to all the grid nodes. In here, what you do is you give an axial velocity of 1 meter per second to all the grid nodes to start with. So that is because there should be a value for all everywhere, and then what you do is next is once you have set up the problem, you run the calculation, and once you so that's when it does the iteration. So before you run the calculations, you need to create the convergence criteria. So in this case, we set the residual size to 10 to the minus 5 here, and then you define the calculation activities, like you run this simulation for only 200 steps, and you let the software output. Sorry, I did a mistake here. You run the simulation for 500 steps, not 200 steps. So the number of iterations you put at 500. And then this is what you see as the residuals. So in here you can see that the problem is converging, meaning residuals are going down. So at start the residuals will shoot up first, and then it goes down. So once you have done the calculation, okay, this is the screen that you get. That means you have got a converged solution. Now you have done your simulation. That means you have solved the physical problem now, the simulation. Now what you have to do is to look at the results. So to look at now, if you look at your ANSYS workbench, you will now see that your geometry, there's a tick against the geometry, that has a tick against the mesh, a tick against setup, and a tick against solution, and no tick against results. That means this is the last thing that you have to do. So you have done all the other work that you had to do to look at the results. So an interesting thing that you can do with ANSYS or ANSYS is that you can plot. You can do surface plots of various surfaces. Now in here, what you see is a cross-sectional area of the pipe with the velocity velocity vectors actually, and these vectors are colored according to the magnitude of the velocity. So you can see that your velocity is increasing through the center. It's increasing through at the center line here, and you can see the entry here, entrance velocity. So this represents about 1 meter per second entrance velocity, and at the walls the velocity is going near 0, and in the center the velocity accelerates. So you have a velocity profile, a high velocity in the center and a low velocity in the, at the walls, or 0 velocity at the walls. So ANSYS allows you to do this, and how to get these plots done is explained in the tutorial itself. So you go to you click results on ANSYS workbench, and then you go to graphics, and then you do a new surface plane, and then you do a create, and then you do the displays, and you give vectors as as explained in here. Just follow the steps that are stipulated in this tutorial, so you will be able to see this plot. And then also you can do a line rake through a center line, and write that data as an xy function. So here what you see is a axial velocity plot against the length. So you can see that the axial velocity in the center line is starting at 1. It will go up near to 2 meters per second. If you can go in here, you can see that your axial velocity starts here at 1 meter per second, and when it goes up to here, it goes to 2 meter, nearly 2 meters per second. You can see that here. And again, setting up of this is clearly explained in the tutorial itself. And then the rest of the instructions tell you how to have gradient, how to have splits in the x-axis, and also you can do other types of plots as well. You can compare your theoretical results of your axial velocity using an analytical solution. So to do the analytical solution, you need to look at your fluids notes. Now here, what you can see is your theoretical results versus velocity results versus your this is actually the radial velocity. Theoretical velocity profile against the CFD velocity profile.